Okay, so in our previous class, we were discussing how diodes work. So today, let's do some example questions on how to deal with those questions. Okay, so example one. Let's say we have a silicon diode. So the forward bias of silicon diode is 0.7 volts, and then a resistor and a 10-volt battery. And a 10-volt battery, 2 kilo ohm. Now here, we know this diode is forward biased. Positive side of the terminal is connected to the anode and the positive negative is connected to the cathode. So it is forward biased. Or you can think like this. Just look, current will be flowing in this direction, right? So this arrow is pointing in this direction. Hence, it will allow current to flow through it. Now here, this will set up a potential difference of 10 volt. Across this, 0.7 volt will drop. There will be a drop of 0.7 volt. Here, a drop of 0.7 volt. Then, the remaining voltage, here we have 10 volts. The remaining voltage will drop across this resistor. So that is 9.3 volts. So, current in the circuit. If we find what is the current in this circuit, we can use V is equal to IR across this. Current will flow in this direction, right? So V equal IR, V is equal 9.3 2 kilo ohm into I. So I is equal divide this one by 2, 4.65 kilo is 10 to the power 3. When you take it to the denominator, it becomes -3. When you take it back to the numerator, you can straight away write it as milliamperes. So 4.65 milliamperes. So we can only use to control the current in a circuit where it involves diodes. The only possible way to control the current is the resistor. By increasing this resistance, you can decrease the current through the diode. Or by decreasing this resistance, you can increase the current through the diode. And if you want to find the potential difference across the diode, then also you can use this formula. I mean this idea, where you will find the potential difference across the resistor and the remaining potential will drop across the diode. Okay. Example 2. Let's say this time we have a germanium diode. And a 5-volt source. So for germanium diode, the forward bias voltage is 0.3. So here this will create a potential difference of 5 volt. And here there will be a drop of 0.3. Then the remaining 4.7 will drop across this. So apply V equal IR to find out the current. 4.3 volts is equal I into 2 kilo ohm. Therefore, I is equal 2.35 milliamperes. We will get the idea how to deal with these types of questions. Example 3. Now let's say we have two diodes. One is silicon, the other one is germanium. Silicon and germanium. So here again these both diodes are forward biased. So here you have 9 volts. The drop here is 0.7. The drop here is 0.3. So across this drop will be 8 volts. Now we can find the current. So V is equal IR. 8 is equal I into 4 kilo ohm. So I is equal to 2 milliamperes. Look at example 4. It's slightly different. Now we have to find what is the current. Okay, have you noted up to the third example? So here, uh, now we have 5 volts. So the potential increase here will be 5 volts. Okay with that. Now germanium, it needs only 0.3 voltage to get forward biased. So this needs only 0.3 voltage. Once this is forward biased, current can flow through this germanium diode only. It doesn't need to go through this silicon diode. Okay. So this silicon diode also will have 0.3 volts because they are connected to the same point, which is not sufficient to forward bias the silicon diode. So the current will flow through this germanium diode and it will only use 0.3 volts. Therefore, the remaining 4.7 volt will drop across this resistor. So if you want to find the current, V is equal IR. So V is 4.7 volts, I into 2 kilo ohm. So I is equal 2.35 milliamperes. Okay. Is the idea clear? Is that clear? Because we know in a diode, soon after it is forward biased, then the current uh, it can flow through increases rapidly, right? The current increases rapidly. When you have a resistance less path, just think this path as resistant less soon as it is forward biased. So this is high resistant, this is low resistant. So the current will choose this path, and now as it can flow through this, it doesn't even think of forward biasing this. Okay. Example 5. We have two silicon diodes. We now find the current through this. This is silicon diodes. Try and check my answer. It's 3.6 milliamperes. State forward bias, reverse bias, or not biased for the following. First, what can you tell about these diodes for the remaining also? So, what can you tell about the first diode? Is it forward biased or reverse biased or not biased? Not biased, let's say in B. So, what can you tell about the first one? Forward biased or reverse biased or not biased? So, this side, I mean, you can consider this arrow. Think about this arrow, okay? From +5 to 0, current will be flowing in this direction. So in this direction, it will allow current, and this voltage is sufficient to forward bias silicon or germanium diode. So this is forward bias. What can you tell about the second one? What can I tell about the second one? Forward bias or reverse bias? Any idea? Forward bias to reverse biased. You can hear me, right? I have to do the remaining also. Saja, what do you say? This is forward biased. We don't look for the potential, we look for the potential difference. Okay, Sarah, here you have 0 volts, here you have minus 10. So current will try to flow in this direction, where this potential difference is 10 volts, right? So zero point 0.7, it can forward bias it. So it is forward biased. We don't look for the potential, we look for potential difference. You should have that idea in mind. And the third one, it is not biased. It is not biased. And the fourth one, here you have 0, here you have minus 1. Current will try to flow in this direction, but this diode won't allow it because it is reverse biased. Is everyone clear with that? Three of you clear with these 4 questions? Sarah, did you get the idea? So I'm okay, right? This is an ideal diode. So in an ideal diode, we know if there is forward bias, resistance is 0. If there is reverse bias, the resistance is infinity. What type of bias is this now? Forward bias or reverse bias? This diode. Okay, the diode is reverse biased. Okay, the diode is reverse biased. Think the current will try to flow in this direction, right? So this diode won't allow it. Then the equivalent resistance, you can just forget this diode. You can just remove this diode, and then our equivalent is going to be 3 kilo ohm. So the current in the circuit, you just omit this, since diode is reverse biased. And now you can apply V is equal IR. 10 volt is equal I into 3 kilo ohm. I is going to be 3.33 milliamperes. Once you have modeled, let me know. Okay, next example. Again, this is an ideal diode. What can you tell about the diode this time? Is it reverse biased or forward biased? It is forward biased. The diode is forward biased. The current will try to go this way, and the diode will allow. Can you remember, for ideal diode, forward bias voltage is 0 and resistance is 0. In the final note, I gave you to note down. In that we have mentioned this, right? So there is no potential drop across this diode, and now it is just like it's short circuit. The 3 kilo ohm, the 3 kilo ohm resistor is no more in the circuit. Okay, so the identical circuit is 9 volt and 2 kilo ohm resistor. You can do like this. 9 volt with this 2 kilo ohm resistor and this ideal diode. So here the current, the 9 volt is going to entirely drop across this resistor because no drop in an ideal diode. So 9 is equal I into 2 kilo ohm. So I is equal to 4.5 milliamperes. Okay. So what is the current in the circuit? Current in the circuit. So here, how about the diode? Forward bias or reverse bias? It is reverse biased. And uh, will there be a current flow in this circuit? There is no any path for the current to flow, right? This 6 volts, this 6 volt potential is going to drop entirely across this diode. It is going to drop entirely across this diode. And there is no any potential drop here. The current flow in the circuit is 0. There is no current flow. Okay. Okay, noted. Find I. This is slightly different. Okay, this question is slightly different. Carefully listen. First, we have a silicon diode. Now, silicon diode, the forward bias voltage is 0.7 volt. If we apply 0.7 voltage, then only this will get forward biased. Unless it will remain not biased, therefore current won't flow through it. Here, what you have to do is, first you must check if this diode is active or not. That means, is it forward biased or not? So, let's find out. Let's find out what is the voltage without the diode. Okay, what will be the voltage between these 2 points? Let's say this is V. this is V. So that will be the same voltage across this silicon, right? Find I is the question. Now what we are going to do is, we are going to find without the diode, what is V? So if this diode is not present here, this is a potential divider circuit. So you can straight away write 6 over 50 into 10. V is equal 6 over 50 into 10. So this is equal 1.2, right? This is equal to 1.2 volt. So the voltage across this without this diode will be 1.2. Now we have the diode. Now, what can you tell about the diode? Is this voltage sufficient to forward bias this? Yes, this is sufficient to forward bias this. I'll say this is V dash. Since V dash greater than 0.7 volt, the silicon diode can be forward biased. So it gets forward biased. Now we will again find the current, or we will again redraw the circuit for this forward bias case. So here, I'm not redrawing the circuit, okay? I'll say without the diode, V dash is without the diode, what is V dash? Here, now let's straight away mark the values because this gets forward biased. When this gets forward biased, only 0.7 voltage will get dropped across this. So here also only 0.7. Here let's consider silicon as 0.6. We mentioned in a note, right? It will vary between 0.6 and 0.7 depending on the doping. So let's say this is 0.6. Then only our calculations will be easy. So here the drop is 0.6. So here also it will be 0.6. Then across this it is going to be 9.4. So to find I, 9.4 is equal I into 44. So I is equal 213.6 milliamperes. The current, now let's say we want to find the current through the, okay, let's change the question slightly. Find I through the diode. Find the current through the diode. So let's take this one as I1. This is I1. Now let's find what is I2. I2 is equal 0.6 over 6. So this is equal, when you divide 0.1, 100 milliamperes. So what is I? This is I. Then we can find I. I is equal I1 minus I2. So when you calculate, you get 213 minus 100, that is 113.6 milliamperes. Is this question clear, or should I explain once again? Those who got this idea clear, can you raise hand? Or if you have any doubt, you may ask. Okay, Sarah, here. Sarah, are you clear up to this? Why we had to check this question in 2 steps, do this question in 2 steps. First, we checked if this diode can be forward biased using this potential divider. Here we have a potential divider, right? Due to this potential divider, we are finding whether it is having sufficient voltage to forward bias this. So we found the potential divider will give us 1.2 volt, which is sufficient to forward bias. Therefore, the diode gets forward biased. Then we go for the forward bias condition. So here, when forward biased, it's 0.6 voltage. So here also it will be the same, right? Because it is across the same pins. If this is 0.6, the remaining should drop here, 9.4. So now you can find the current through each of the resistor, and using the KCL, current law, we can find what is I. Okay, Sarah. Shahama. Shahama, are you clear with the idea? Okay, the meeting might end. I will put a question in the group. Try that until the meeting gets recorded.